So what we're going to look for is an alternative that has higher accuracy and fewer computations. Here's how we're going to do it. We are going to have our trajectory, and it's going to depend on the angle. So I'm going to have one angle here, let's say 85 degrees. Let's go 85. 85. I know that's going to come up short. Here's 35. My target's out here at 35. I know 85 is going to come up short. I know some other value is going to go too far, so let's go to 45 degrees. It'll be too far. So one of the things we can do is meet in the middle. We can say, all right, halfway in between might be a reasonable place to start. So if we start at halfway between, would be 65 degrees. Let's make that red. So if we launch at 65 degrees, that actually, we can actually do that for a second. I'm just going to try that. And I'll take out this if bit. Run. So that lands a little short. So 65 degrees lands just a little short of 35. If I was looking for an interval of angles, 65 is too short. What angle is too far? 45. So the right angle, this is totally Goldilocks, right? This one's too short. This one's too far. The one that's better is right in the middle. So why don't we go halfway between the 65 and the 45? We'll go 55. So we can cut that in half again. But the key thing I want to point out is we're going to take one of each kind of outcome. One that's too close, one that's too far. As long as I keep that idea, I can always hone in on the solution, which is the exact value. Now 55 degrees is definitely going to go too far. So here's 55 degrees. It's going to be too far. So I'm going to go halfway between the 55 and the 65. OK, 60. And you can see that I can certainly narrow in on the bracket very quickly. But if you actually think of the math, I've got an interval of 20 degrees, then 10, then 5, then 2, then 1. In about 6 steps, I've gotten down to less than 1 degree. I've got the answer to within 1 degree. When I did the loop, it took me 90 steps just to cover the frickin' territory, or 900 if I wanted to go by 0.1s. So with this bisection, we can very incredibly quickly narrow down the window of possible angles. It's very, very efficient and very, very accurate. So we're going to try to code that up. But the idea is something that's too far, something that's too close, stay in the middle of those things, and you'll be able to get the right angle very, very quickly. And let's see if we can code this up. So we're going to save what we started with as a new file. Actually, I'm going to undo all that stuff there just so it looks like it did before. Fantastic. And we'll save that as W42. All right. Delete. So what we're going to have here is 2 angles. One's 45 and one is 85. So these are the bracketing angles. One leads to too far and one to too close. Actually, it should be more specific. B leads to too close. Now I'm going to build this up as a piece the way I would like to build it up. I'll explain as I go, but I think there's a bunch of things that have to go in at once. This one's a little less incremental in the way we can build it. But the idea is I'm going to shrink that angle. So it's going to be 45, 85, 65, 45, 45, 60. I'm going to take those A and B values and update them. So what I'm going to do is say while, keep doing things, while the difference, and let's keep this clear, while B minus A is fine, is larger than 0.01. So this means keep going until the angle is known within plus or minus 0.01 degrees. If you look at what we started with, they're 20 degrees apart. So while 20 is bigger than 0.1, yeah, 20 is bigger than 0.1. Do this thing. Make it better. Shrink the interval. We're going to tweak A and B. We're going to come back. They'll be half as close or twice as close, half the distance. And that B minus A is eventually going to shrink down, but at the beginning it's going to be big. We're going to try to do our calculations until it gets small. So that while can be a little counterintuitive, but bear with me. All right. So what we're going to have to do here is a little bit of work. All right. We've got our x impact. And what we want here is just to modify, actually, this if statement's perfect. It's lovely. Is less than the target x target. All right, so this is the too close. All right, so let's say we do this. We're going to do a calculation. We're going to launch, but we're too close. Let me go back to the picture on the slides and explain what we're going to do with that. If we end up too close, then we can throw away the 85. The 85 was too close. I've got a better too close argument now. So we're going to throw away the 85 and keep the new angle. So our 85, I think, was our B. Our 85 was our B. So our B is going to equal, oh, wait. There's one more ingredient we're missing here. I'll put it in a second. Something called C, and else A is equal to C. Too far. All right. So let's go back a little bit here, up to the top. There we go. What we're going to do is do that bisection. C is going to be the average of A and B. This is the midpoint. Midpoint, or the bisecting angle. Now, the most classic mistake I see when people code this up is to confuse the two things, those two lines at the top. The first one is how far apart A and B are. B minus A, how far is this gap? 20 degrees to start with between those two numbers. The next one is, hey, what's the midpoint between 45 and 85? Well, I add them together. I take the average and divide by 2. So I add them, divide by 2. That's how you get the midpoint. So don't confuse those two things. Then the only thing I have to do here is change all my theta naughts to C's, because now that's a C value. And down here, same thing. Everywhere I see a theta naught, it's going to be a C. And that should do nicely. And I think that's it. So let me unscroll this a bit so we can see as much as possible, walk through the logic for a second, and then we'll see how that works. There we go. So first time through, B and A are 45 and 85. We're going to split the difference, call it C, 65. Launch 65. We're going to do all the calculations we did before, and then we're going to ask, hey, did I get too close? Well, if I got too close, that's my B angle. I can throw away the 85 and say it's too close if I use 65. So let's go between 45 and 65. Then we're going to take the midpoint there. And then we're probably going to be in this too far category. Oh, too far. Well, I had too far is 45. Now I can replace that with something that's closer to the target, but still too far. And if we do that a bunch of times, we should hone in quite nicely. And let's do this. Let's put the angle and the landing point, x landing, x impact. And those are C and x impact. The only thing I didn't set was the target. I'm just going to hardwire it at 35 there, like so. So we're going to run it, and then we're going to see if there's any conceptual challenges. First, we're going to make sure it runs, though. Oh, brilliant. Brilliant. This is exciting. All right. For me, anyway. All right. Look at that. We said halfway between 45 and 85 is 65. OK, so that was too short. So we do it a little bit longer. You can see the honing in. And you can see that it took like 12 iterations to get 3 digits of accuracy. So the angle accuracy is ludicrous. It only took 12 steps to do it. And we're closer to the impact point as a result. And we can even tune that a bit better if we want. We can go back and say, well, let's get the angle within 0.001 and see how long that takes. It's not going to take long. Everything else is fine. We'll add a few more digits to these guys just so we can see the result. And brilliant. So it takes a few more steps, not many more. I'll scroll it up in a sec. But 64 point blah, blah, blah gets me within 0.06 millimeters of the target, and is not a whole lot of computational work. How many iterations did it take? How many steps did it take? Less than a page full. So thinking back to the linear stuff, when we see a win-win, this is a win-win scenario. This method does not take many iterations. Awesome. It wasn't that complicated to code. So compared to the loop structure being complicated and trying to customize it, this is actually pretty straightforward. And the accuracy is ludicrous for the number of steps that we took. The trade-off there is great. So it's actually a win-win-win.